Hello, everyone. Welcome back to my channel. I'm your academic coach, Yuhyun. Today is day 8 of AP Physics 1. Today, I'm going to go over a really important concept in kinematics, free fall. Free fall is one of the most important one-dimensional accelerated motion that you will see over and over again in kinematics. So Galileo is the very first one who proposed the idea of free fall. Before him, many people believed that objects drop at different rate depending on their weight. People believe that heavier objects such as metal or stone drop faster, while lighter objects such as a piece of paper or a clothes or feather drops at a slower rate. And Galileo proposed the idea of free fall, and then he suggested that any object drops at the same rate no matter of their weight. And he performed that really famous experiment of Leaning Tower of Pisa. So he brought two spheres, one metallic and one wooden, and then he dropped these two spheres at the same time. And the result is two spheres dropped at exactly the same rate and they reached the ground at the same time, even though the metallic sphere is much heavier than the wooden one. So he proves that any object drops at the same rate. Well, now we know that there is a very important condition for this. For any object to drop at the same rate and goes through free fall, it needs to experience force of gravity only. And the reason that these two spheres drop at the same rate is because they have about the same size and the same shape. So the amount of air resistance they receive is about the same rate. So in reality, on the Earth, because of air resistance, there is no true free fall unless you are gonna put that object into an evacuated tube. That also explains why when you drop a feather and a stone, in reality on the Earth, the feather drops at a much slower rate due to more air resistance. And the amount of air resistance an object receives depends on its material and its shape. So a feather has obviously a much larger surface area, so it receives a lot more air resistance. So for stone, it's going to receive only a small amount of air resistance. So that explains why the stones drops at a much faster rate. But if you put them into an evacuated tube, no matter of their shape or material or the surface area, they will drop at exactly the same rate. This idea can also be proved when you drop a stone or and a piece of paper at the same time. If it's just a flat piece of paper, obviously the paper drops at a much slower rate due to larger surface area and thus larger air resistance. But if you fold it into a crumpled paper, then now they have about the same shape, even though it's different material. So they experience about the same air resistance, and thus they are going to drop at about the same rate. So in AP Physics 1, we are going to assume that there is no air resistance in most of the cases, unless it states in the problem that there is. And we are going to assume that any type of motion that an object experiences in air is free fall. So in Unit 2 in dynamics, you will learn that actually objects of different weight experiences different amount of gravitational force. But what they share in common is that no matter of weight or size, they experience the same gravitational acceleration. And this is the key for two objects to drop at the same rate. So gravitational acceleration on the Earth is 9.8 meters per second squared, and it points downward. It's often represented as g, lowercase g. So this value can be different depending on the planet. Let's say on the moon, that's only one sixth of the gravitational acceleration on the Earth. That's approximately 1.6 meters per second squared. So this is how the motion diagram of any freefall object looks. If you drop it from rest in the air, then it's temporarily at rest at the very beginning and then it gains speed over time. If you toss an object vertically upward, then it would slow down due to acceleration that points in the opposite direction, and it will reach the max height. And at the max height, it temporarily comes to a stop, and then it switches direction of motion and starts moving down. And while moving down, it accelerates. What if I toss an object vertically downward? If an object is given an initial velocity that points downward, then while it moves down, it's gonna speed up even more. So again, it does not really matter what the initial velocity of free falling object is. What really matters here is that for any free fall object, they experiences a downward gravitational acceleration of the magnitude of g. Here, I'm going to show you a few free fall tricks that you can use to solve free fall questions very quickly. None of these equations are new. They're all based on four kinematics equations that you've learned before. So if you understand how to use four kinematics equations or how to apply motion time graph, then you should be able to derive these as well. The first scenario is when an object is tossed vertically upward and eventually reaches its max height. And we know that when an object reaches its max height, it temporarily comes to a stop. So final velocity is automatically zero. Well, this is initial velocity that points upward. And if you want to know the h max, which is the height difference between initial height and that max height where it comes to stop, then we can immediately apply 1 half gt squared, where t represents the amount of time it took for the object to move from initial height to the max height. And we can derive that formula by using kinematics equation 2. Kinematics equation 2 states that delta x displacement is equal to v initial times time interval delta t plus 1 half a delta t squared. Here I'm going to replace delta x with delta y because it's vertical displacement. And here I'm going to use v final instead of v initial. If I use v final, then it's subtraction of 1 half at squared. And since v final and since it's an upward motion, so we are going to take upward as positive direction and downward as negative direction. Then throughout this free fall motion, acceleration is negative g since it points in the opposite direction of velocity. So for acceleration here, we need to plug in negative g. Then we get delta y is equal to 0 times delta t minus 1 half times negative g times delta t squared, which is positive 1 half g delta t squared. That's how we got that free fall trait of h max, which is basically the displacement, is 1 half gt squared. And second free fall tricks that we can use would be finding the initial velocity just based on the height or just based on the time. So it could be either square root of 2gh max or it could be g times t. So we can get the first one, v initial is equal to square root of 2gh max by applying kinematics equation 3. V final squared is equal to V initial squared plus 2a delta x. V final squared is again equal to 0. Acceleration is negative g. I'm going to replace delta x with a delta y. Then we get that V initial squared is equal to 2g delta y. And again, delta y is this displacement that points upward, so we can replace that delta y with h max. And if I take square root on both sides, then I get V initial is equal to square root of 2g delta y or square root of 2g h max. So if you toss an object upward and eventually it comes to stop at max height, then just based on the height, I can already figure out the initial velocity. What if I don't know the maximum height, but I only know the time it took to reach the max height? Then you can directly multiply g, gravitational acceleration, to time to get initial height. And that is from kinematics equation 1. Kinematics equation 1 states that v final is equal to v initial plus acceleration times delta t. V final is equal to 0. Acceleration is negative g. So v initial is equal to g times delta t. Just remember that these free fall tricks can only be used when an object is tossed vertically up and when it reaches its max height. So its final state is max height, and its final velocity is 0. That's the condition to use these free fall tricks. Next, there are two more free fall tricks that will be very, very useful. This time, imagine that you toss an object vertically upward, and after it hits max height, it comes down and it returns to its initial height. This is how its motion diagram looks. In that case, the amount of time it takes for an object to reach the max height from initial height, t up, is the same as the amount of time it takes for an object to return to the initial height from max height. So t up is equal to t down. And also v initial and v final has the same magnitude. They just points in the opposite direction, one vertically up and the other one vertically down. And we can prove these two at the same time using motion time graph. Here we're going to draw a velocity versus time graph for this free fall. So initially, v initial points upward. It means v initial is positive. Let's pick a random point right here and state that as v initial. Throughout the whole process, we know that it's free fall. And for free fall, what's really important is it experiences gravitational acceleration, which is constant. It always points downward at the same rate, 9.8 meters per second squared. And we know that acceleration is the rate of change in velocity. So it's shown as the slope on velocity versus time graph. Constant acceleration means that velocity versus time graph is a linear line. And since it's negative, this means that it's a linear line with negative slope. Now we know that this part represents t up and this part represents t down. Now let's take a look at these two right triangles. This part represents the motion of the object moving up until it reaches max height. This part of the graph represents the motion of the object dropping from max height back to initial height. Eventually, it's back to its initial height, which means that throughout this process, if you combine both of them, then their displacement, total displacement, add up to 0. So delta x up plus delta x down, this is delta x up, this is delta x down. These two displacement add up to a total displacement of 0. And that is shown as the area under the graph of velocity versus t graph. That means that the area of this yellow right triangle and the area of this blue right triangle should add up to 0. And since one of them is above t-axis, it's positive. The other one is below t-axis, which is negative. Okay, that means that these two triangles have the same area. The only difference is one is positive, the other one is negative. And since they share this linear line as their hypotenuse, this means that these two angles are the same. Eventually, that means that these two right triangles are congruent to each other. That proves that t up is equal to t down. So the two bases of the right triangle are congruent. And that also means that their height is the same. Since VF represents a negative value, the height should be negative VF. That's why V initial is equal to V final. So again, when you toss an object upward and after it reaches max height and comes back to its initial height, T up is equal to T down, and initial velocity and final velocity have the same magnitude but opposite direction. Let's do a few practice problems to make sure that you can use those free fall tricks that you just learned. Question number one. A ball player catches a ball 3.0 seconds after throwing it vertically upward. With what speed did he throw it and what height did it reach? So this is the motion diagram of this ball. The ball is tossed upward. It reaches max height, temporarily comes to a stop, and it moves downward until it's back to its initial height. And the whole process took 3.0 seconds. We know that T up is equal to T down, and these two add up to 3.0 seconds. That means each of time interval is 1.5 seconds. We want to know what speed he threw it. That means we want to find V initial. We know that by using free fall tricks, V initial is equal to square root of 2gh max, or it's equal to g times t. And here, t represents either t up or t down. So since we're given time, we can use gt, and that would be approximately 10 meters per second squared multiplied by 1.5 seconds. So approximately 15 meters per second. That's how fast he threw the ball upward. And what height did it reach? So it's asking for max height this time. And we know that H max, by using free fall tricks, is equal to 1/2 gt squared. And again, this t represents either t up or t down. So 1.5 seconds. 1/2 times 10 meters per second squared times 1.5 seconds squared. That is 11.25 meters. So now you see that by using free flow tricks, we can very quickly get the answer and get approximation. Question number two. A baseball is hit nearly straight up into the air with a speed of 22 meters per second. So this time initial velocity is given. How high does it go? Okay, so again, for how high does it go, it means that it reaches the max height where it temporarily comes to stop, where V final is equal to 0 and V initial is given. And we know that H max is equal to 1/2 GT squared. It's just that for this one, we can't use that trick. But think of it, since we are given V initial, and V initial is equal to GT. That means T is equal to V initial divided by G. So 22 meters per second divided by 10 meters per second squared, 2.2 seconds. That's how much it took for the ball to reach its max height. So now I can plug this in back to H max equation. Then I get 1/2 times G times T squared, which is 24.2 meters. So this would be the max height. B, how long is it in the air? Where we already got the T here again. This T means either T over T down. That's equal to 2.2 seconds. So when it comes down, T down will be exactly the same, 2.2 seconds. That means T total would be twice of them, so 4.4 seconds. Question number three. An object starts from rest and falls under influence of gravity. So this time, the object starts at its max height. It starts with initial velocity of 0 and it speeds up while moving down. Draw graphs of its speed and the distance it has fallen as a function of time from t is equal to 0 to 5 seconds. So first off, let's determine which direction to take as positive direction. Since the object only moves downward, and its velocity vector all points downward, other than the initial velocity, which is zero. And it experiences gravitational acceleration, which also points downward the whole period of time. So it will be reasonable to take downward as positive direction. So acceleration is positive g. And we should try to draw velocity versus time graph. Since free fall is a constant acceleration motion, this means that on velocity versus time graph, I will see this linear line with a constant slope. And here the slope is a positive because I took downward as positive direction. And initially it starts from zero. That means when t is equal to zero, velocity is zero. This graph starts at 0, 0. So this is how this graph looks. It's a linear line with positive slope. And since speed is just the magnitude of velocity, so I can replace that y-axis with speed and the graph looks exactly the same. Now we need to draw the distance it has fallen as a function of time. So the distance, the physics quantity relevant related to distance would be displacement. And for displacement, we know that we can use that free fall tricks. H max is equal to 1 half gt squared. So this is usually used when an object is tossed upward until it reaches max height. We can also use that when an object is dropped from rest, from a height to the bottom. So the distance it has traveled is the same as h. So if we draw it as a function of time, it will be a quadratic function with a coefficient of 1 half g. Next, question number 4. If air resistance is neglected, show algebraically that a ball thrown vertically upward with a speed v0 will have the same speed v0 when it comes back down to the starting point. So previously, I showed you that v initial and v final have the same magnitude but opposite direction by using motion time graph. That's the easiest way to show that. But we can also show it algebraically. So this is the motion time graph of an object that's thrown vertically upward and eventually coming down, coming back to the initial height. So throughout this freefall motion, object experiences acceleration that points downward. Since v initial points upward, so let's take upward as positive direction. So acceleration is negative g this time. This is initial position. This is final position. So that means delta y, displacement, is equal to 0. So we know acceleration, we know delta y, and we want to know the relationship between v initial and v final. So by applying that kinematics equation table, we have 1, 2, 3, 4, 4 physics quantities, and we can use kinematics equation 3. V final squared is equal to V initial squared plus 2 times acceleration times delta x, or delta y, that displacement. So V final squared is equal to V initial squared plus 2 times negative g times 0. This means V final squared is equal to V initial squared. So we can show that V final and V initial have the same magnitude. Absolute value of V final is equal to absolute value of V initial. Next question. A bowling pin is thrown vertically upward such that it rotates as it moves through the air. Initially, the center of the mass of the bowling pin is moving upward with a speed v initial. Represent the max height of the center of the mass of the bowling pin in terms of v initial and g. So it does not really matter if the bowling pin is moving straight up or if it's rotating. What really matters here is that the center of the mass of this object is moving straight up. So we only need to consider the center of the mass. So this would be the motion of that the center of the mass of bowling pin. And by using free fall tricks, we know that the max height of center of mass, h max, can be represented using 1 half gt squared. The only thing is here, it asks us to represent it using v initial and g. And now we can also think of another free fall trick equation, which is v initial is equal to square root of 2g h max. And in this equation, we see v initial, a constant, g, and h max. So we can rewrite this to represent h max. By squaring each side, its v initial squared is 2gh. And by isolating h max, we get that h max is equal to v initial squared over 2g. So this would be the answer. Question number 6. A planet has an acceleration due to gravity of 4 meters per second squared. So it's not Earth. An object is released from rest from a cliff and it lands on the ground in 20 seconds. A second object is then thrown upward from the same cliff with a speed of 4 meters per second. What is the time it takes to reach the ground? So, first off, an object is dropped from rest, and then it took it 20 seconds to reach the ground. For the first object, since it only moves downward, all of its velocity vectors points downward, and its acceleration vector points downward. So let's take downward as positive direction. And we know that for h max, it's equal to 1 half gt squared. So it's 1 half times 4 times 20 seconds squared. So it's 800 meters, which means the cliff is 800 meters from the bottom. And then this time we have second object that's thrown at the same cliff at the same height, but with an initial speed that points upward, that's 4 meters per second. So this is how the second object motion diagram looks. It's asking us how much time it takes to reach the ground. For this one, we cannot use those free fall tricks anymore because in this case, this object is not tossed up until max height or it's not just back to the same height. The initial height and the final height is different. What we know for now is we know the displacement. We just calculated h max. So we know that delta y is equal to negative 800 meters. And this time, since initial velocity points upward, so I'm going to take upward as positive direction. So its acceleration is negative 4. So we know acceleration, we know initial velocity, we know displacement, and we want to know time interval. Then using one of the four kinematics equation, then I should apply kinematics equation 2. Delta y displacement is equal to v initial t plus 1 half a t squared. Now I'm going to plug in all the numbers. Negative 800 is equal to 4 times delta t plus 1 half times negative 4 times delta t squared. So negative 400 is equal to 2 delta t minus delta t squared. I can rewrite it as delta t squared minus 2 times delta t minus 400 is equal to 0. Then I can get that delta t is equal to then by using quadratic formula, then I can get that delta t is equal to 2 plus minus square root of 1604 divided by 2. Since delta t cannot be a negative value, so I can only take 2 plus square root of 1604. So delta t comes out as 21.0 seconds. That's the amount of time it takes for the second object to eventually reach the ground. Question number 7. An object is thrown with an initial speed v near the surface of Earth. Assume that air resistance is negligible. If the object is thrown vertically upward, the direction and magnitude of its acceleration while it is in the air is. So, this is a question that just tests on your understanding of free fall and gravitational acceleration. So, again, this is how the motion diagram of any free fall looks when you toss the object vertically upward. The velocity changes. Velocity gradually decreases over time until it reaches zero and until it switches sign and becomes negative. And we know that throughout the whole process, it experiences gravitational acceleration that points downward. And that's always consistent. That's always constant. So the acceleration is always downward and constant. Velocity will be changing. Velocity switches from pointing upward to downward. Velocity's magnitude also changes. But acceleration does not change at all. It does not switch direction. It does not change its magnitude.